So this is an ongoing work which I am doing with my collaborators, Vijay Sai and Professor Rajiv Jain from JDC. And I would like to thank the organizers for this opportunity for presenting this work here. I start the discussion by just giving a brief motivations on the cosmological correlators and the method which we are going to use to compute these correlations, which will be the Indian formalism. And both these things are almost covered in this yesterday's talks and everything. So I will be just going very briefly on this. Then I will go on to the model which we are interested in, which is the U1 gauge field in the inflationary background. Once we are done with that, we will go and compute the 4-point autocorrelation functions, and the cosmological diagram which we are interested in computing, this as shown, and this is, you can view it like there is some process happening during the time of inflation, and we will be measuring the correlations at the end of inflation, which is derived by eta naught, and all this will be in the conformal timing. Then I will show some of the results we have at the current stage, and we will discuss the possible consequences of this. As I already mentioned, we will be working in the calculating the higher point functions, or the specifically 4-point autocorrelation functions during the time of inflation, with the hope that this can shed some light into the inflationary scenarios, whatever is happening during the time of inflation. And these kind of higher point functions are computed already for tensor and scalar perturbations specifically, but computing this for other fields like the gauge fields or other fields in the standard model will also be interesting. And specifically in this context, we are focusing on the U1 gauge field, and they look on whether these kind of 4-point functions can give us an intuition about the primordial magnetogenesis. Specifically, the models which we are going to use in this analysis will be the one which are simple ones which are going to use, which people are used in order to understand the primordial magnetogenesis, like the Ratra coupling. So with that, I will move on to the mathematical tool which we are going to use in order to compute these autocorrelation functions, which will be the just Inning formalism or the Schiller-Keldysh formalism. So this formula is also shown in this meet several times. This is just the way to compute the Inning correlators, and the things to note is actually the operators here are time ordered and this is time ordered, and this will be the complete vacuum we are interested in. This will be the free vacuum with respect to which we are computing this thing. Just one more thing I just want to highlight is actually related with the calculations of this thing, and we have to keep track of the order of these things. The blue part I show is lives on the blue contour, which is a different contour than the red one, the time order things. Because this, if you are not keeping track of these things, this can cause various divergences in your analysis. This has been shown, and this will be there. Basically, the point is we have to keep track of the contour properly, so that it will be going to the properly bunched Davis pattern. And since we are doing perturbative analysis order by order, if you are just going beyond some first few orders, things will get messier, and keeping track of this will be a bit tedious. And one good way to do that is actually using the cosmological diagrammatic methods, which is something we are going to follow in this analysis completely. So with that, now we are moving on to the model which we are interested in doing this analysis. This will be just the U1 gauge field working in the inflationary scenarios, and mostly I will be working in the conformal timing with this sort of metric. And since we are looking at the magnetogenesis, as we know that there is a very weak correlated magnetic field in the entire universe presence, in order to explain that, one of the good models is having a primordial origin. So if it has to be amplified, the standard magnetic field which we are interested in, that is conformally symmetric. So this has to be broken. Like for the amplification of this thing, conformal symmetry has to be broken. So the model which we are going to use, or current time used, is actually the electronic coupling or the kinetic coupling, which is called the Raja coupling, and which actually explicitly broke the conformal symmetry in the system. And other more constraints we are actually assuming that the lambda will be going as a monomial functions of A, the scale parameter here, and which is actually given as this form in the terms of time, conformal time. So this model is several times explored in the literature, and we know quite a bit about these models. And one thing we know is actually for n is equal to 2 and n is equal to -3, this model is able to produce the magnetogenesis, required scaling wide and required magnetogenesis just using the inflationary scenario itself. And another things we know is actually for n is equal to minus 1, minus 3, this model has problems. It's a back reaction problem. That means the energy density of the electric field starts growing and it will outgrow the background energy density. So the perturbative assumptions will be broken. And for is n is equal to 2, there is no back reaction problem, but we have another problem which is the strong coupling problem. And in the time of inflations, the coupling of electromagnetic field will be very strong, and that also breaks our predictive powers on this flow. So these two problems are there, but they have way around some of this problem, but still there. That means we have only two things like the 2n is equal to 2 and n is equal to minus 3 will be more interested to us also in our analysis also. Another thing I want you to notice is that there is no self-coupling for the gauge field here. These are just, there is no self-coupling since we are imposing the U1 symmetry impact. So the only interactions the gauge field can have is through the inflaton, which will be the lambda of phi here, or through the metric perturbations. And we are specifically choosing the co-moving gauge in this system. So which makes the system only possible interactions for the gauge fields will be only through the metric fluctuations or the metric perturbations we are considering. So once we set these things, next question we should ask is how this actually is interacting. That means we really need, in order to use the Indian formalism, we really need the interaction Hamiltonian at the order which we are interested in. So that's the next thing. For that, the one standard way to do that is this thing, ADM decomposition. Basically, we are foliating the space-time into space and time and decomposing this into laps and shifts. And this laps and shifts as not a dynamical variable, constraint variable, which we can solve. This constraints equation can be solved order by order. This is the leading order solutions, and this will be the order which we are working here. And at this order, we can put this back to the action or the electromagnetic action and compute the interaction Hamiltonian at the cubic order, which zeta A coupling with the scalar. Zeta will be the scalar fluctuations and gamma will be the tensor fluctuations, and this will be the interaction Hamiltonian at the cubic order, which we are going to work with. Yeah. Okay. So with that, the first thing one can calculate is the bispectrum, which is already calculated in the literature, and people have shown that there is actually log divergence. When eta is going to very small values, this will get diverged actually. But this is not a problem at this level, but this can be a problem if we are going beyond these things. And that's exactly what we are doing. We are going to calculate the proposed autocorrelation functions here. This will be the topological diagram we are studying. And the complete set of diagrams by interchanging 2 and 3 kind of thing will be this complete spectrum. So we have to calculate this complete diagram values. And schematically the results will be like the proposed diagrams will be like this. We just have to compute these things. This real part comes because you have to account for the mirror symmetry, reflection around this line. So we have to compute. In general, the results looks like this for scalar and tensor decomposition. The Q's are the part where all the polarization is gone, polarization of the gauge fields and the polarization of the electromagnetic field, everything is encountered. And IAs will be the next time integral. And this will be same for all the non-trivialities, so going from zeta and gamma will be encoded in the Q, and all other things will be, or IAs will be same for here. That will be the next computation. And we computed this for different values of n and for different limits of case. And just to note that there will be spurious divergence if you are computing this individually, but if you are computing everything together, this will get cancelled. And I will now list some of the results we have here. Basically, if you just keep all the case arbitrarily, this will be a bit messy. So we will first look at the equisided quadrilateral. That means all case will have same magnitude. And now the A's are always the auxiliary fields. The things we are interested in, which will be the electric and magnetic field, which can be computed from here. And in this equilateral equisided quadrilateral, you can get a general expression like this, where these Q's are the quantities which encodes the information about the polarizations, and I's are the same. At this level, I's looks like this. It will be a function, just a polynomial functions of Q's, log and polydialog. All other things are same. It's polynomial functions. We have these things. And at this level, the quantities from the polarizations will look like for the scalar exchange. One thing I would like to note is that there is only dependence of theta 1, 2 and theta 3, 4. There is no angle dependence between these things, and these diagrams are in the 3D, not a planar diagram. So once we set the ki kind of things, we can fill the categories in the 3D. So for this is scalar thing, and for tensor this will be bit messier, because in tensor case you will have the polarization coming from the gamma ij also. So this won't be this close to the single expression. So there will be theta dependence for all the momentum. So this will be messy, but this thing what I wrote here is actually more general kind of stuff, because I can't get a very close. We can get actually, it will be very close like this, and pi's will be just like the projection tensors here. So this will be true for all the cases, and much more simpler limits which we can nicely see the results will be the countercollinear limit, where we assume that the exchange graviton or theta is going in the very IR, that means very low momentum kind of things. At that point we can write the open order correlations like this, just like in terms of power spectra of theta and beta, where there will be a constant kind of CBNL kind of thing. Same thing for the tensor exchange. As I mentioned, for the tensor exchange there will be theta elements will be a bit complicated, but at this limit we can write like this way. And this kind of structure actually shows us there is this equivalent to soft theorems for the four-point autocorrelations function, which themselves has their own interest. So with that, this is all for n is equal to 2 case. Whatever results I show current now is for n is equal to 2 case, and now we will slightly extend to other n's, or I will just comment on the results for other n. For n is equal to 2, we see everything is finite. There is no problem coming up because of the expected divergence. This is true for all minus 2, 1 and 2. This will be fine. But once you go for the n is equal to minus 3, which is the another scaling, which is the regime where we are getting another scaling variant result, there is actually log divergence coming. That means if you are going to eta not to very small numbers, this will start diverging up. So this regime is problem, and the same behavior pattern goes for higher values of n also. As we start increasing n, the polynomial and higher polynomial degrees of divergence as we go closer to eta naught tends to 0 limit. And this actually means that we have to check carefully about the perturbative validity of these theorems, because the first order corrections will be very finite, and as you go next order, this is actually getting divergent kind of things. And for n is equal to minus 3, we already know there is a back reaction problem. This also adds up to that. And for another, only other model which we have this scale invariant structure is n is equal to 2 case, there we have the strong coupling problem also. So yeah, that is it. That's a summary, and thank you.